Hello everyone, this is Aida from Agrimath Research Company, and in today's video I'm going to teach you how to analyze the regression outputs of the Excel. So as you can see here, I have two sets of data. One of them is observed and simulated data, and the second set is about GPA and SAT results. So in the previous video, I had a clear explanation and actually comprehensive explanation about how to get the regression formula in Excel. If you have not, and if you want to, please go and watch it before this video, as you should know those tips and things before going through these notes. But here I want to do a quick review for those of you who did not watch the previous one, so that you can see how to get that regression formula, and then we get to work on that. So as I mentioned before, there is a difference between correlation and regression. For correlation, we have something like this, that we want to get the strength of the relationship between these two sets of data, not the causality. We are not watching the causality, we are not studying the causality. But in the other sets, which we have a causal relationship, we get to know also the strength of relationship, and also the power of each independent variable on the dependent one. So in here we have GPA results, and we want to know whether the GPA results are affecting the SAT scores. Okay, so what we did was that so before that we mentioned that we can get the regression formula just using a chart. So I'm going through it. I select both of them, go to insert and go for insert scatter plot, and then I go for adding a trend line. Then I go for more options, and in here I go for display equation on chart. So this is the regression formula shown for you, and then this is the regression line, of course. The other way, which is more informative, is to go for data and data analysis. So I go for data analysis, and then I go for regression. I click OK, and then for Y range, my Y range is SAT. The Y range is of course the ones which are dependent, okay? And the X range here is my independent variable, which is GPA. Okay, so then I want to include the labels, and output range is, I wanted to start from, let's say, here. So now you can see this output tables are made for me. The first one is a regression statistics, and the next ones are Anova Table, and the next one, which is the most important table for us. So starting from top, you can see here is said the regression statistic. First one is multiple R. So the first one is multiple R, which is the correlation, the coefficient of correlation. Okay, so coefficient of correlation, or R, as you know, has dimension and varies from minus 1 to positive 1, and minus 1 indicates the strong reverse relationship between two sets of data. And in minus 1 we know that whenever the y data is big, our x data is so low, and as y goes down and y gets this much low, our x gets this much large. Okay, but for plus 1, what we have is a strong direct relationship. So what we mean is that whenever x goes up, okay, y also goes up, and wherever x is down, y is down. Wherever x is up, y is up. So that's the ranges and meanings of these numbers for coefficient of correlation or multiple R, which you can see here is plus 0.63, which is not that bad number, and it can indicate the direct positive relationship between two variables. The next one is R square. So R square, as it seems out from the name, is this indicator, and this does not have any direction. It just changes from 0 to plus 1. Of course, 0 means there is not meaningful or significant correlation between these two sets of data, and positive 1 indicates there is a strong, meaningful, significant relationship between these two sets of data. So here it's 0.40. It's not that much good, so we can say there is not that much significant relationship, but still it's not that bad. Okay, so based on the the accuracy of your data, this also could be a really good one. Okay, so you cannot judge just based on the raw data. You should know other information to judge whether this R square is good or not. But the next one you can see here is adjusted R square. So adjusted R square also indicates the strength of the relationship, but the adjustment is made because of the number of independent variable. So this indicator just operates so good that it takes only the good ones. Okay, so if you have just thrown a bunch of not that much good independent variables in there and you want to make the regression, it can understand that these independent variables are not playing a meaningful role for guessing the dependent variable, so it gets down the R squared. Okay, so it can, in the best way, it's equal to R squared, but it's always smaller than R squared. So this one adjusts itself based on independent variables. So if the quality of independent variables for predicting the dependent one is good, it goes up, and if the quality is bad, it goes down. Okay, so the next one is standard error. This is the error we've made in predicting the y values, and this is the distance between the modeled values, the model line, regression line, which you can see here, the difference between model line and the real values. The next one is observations, which we have 84 number of observed data. Okay, so this is simply the number of data. So let's get to the other table. So this was just a simple summary of your output. This does not actually have a meaningful data in order to evaluate the regression model. Okay, so let's get to the next one. So next one is the Anova table in regression output. So for this Anova table, you get the first row as regression, the second one as residual, and the third one as total. So we know that total y is modeled y plus error. Okay, so we have some data, we can get some of them in the model, and we cannot get the others. Okay, so our model cannot cover all our data. Okay, in reality, we cannot make any model that gets all the data in the data set. So we can get, in some points, we can get some of the data, we can model them, we can show them by model, but we cannot get all of them. And this Anova table shows the sum of squares for regression line, for regression model, and sum of squares for residuals, okay, for that errors. And then there is sum of squares for total. And if here you want to know the r squared, you can simply divide the modeled sum of squares by the total sum of squares, and you can see this number is the same as this one. As we say, logically, as we define the r squared as the part of the data that is represented by the model. So this is model divided by the total. Okay, so that's for sum of squares. And for mean squares, you can see actually this is division of sum of squares by degree of freedom. Okay, and for degree of freedom, for regression, as you had two variables, this is 2 minus 1, which gets you 1, and then we have the same type for residuals, and the total is sum of regression plus residuals. Then we divide the sum of squares by the degree of freedom, and we get mean squares. And the next one, you can see F statistic. So this F statistic is gained by dividing mean squares to each other, and then based on that F square, based on that F statistic, we get this significance F. This significance F is that p-value that we have. This is the p-value related to F statistic. Okay, so As you know, we make a test, we run a test, we get the statistic, and then we get that statistic into those sheets, and we get the p-value based on that statistic that we have calculated. Okay, so we have the p-value as small as this number. So as you know, we have a p-value, and then we compare it to the alpha. And what is alpha here? It's 5%. Why? Because here we are making all these calculations based on 90% level of confidence. Okay, so we get to compare this p-value to 5%. If it's lower than alpha, we know that our results are significant enough. Okay, so there is a significant relationship between these two sets of data. So let's get down. Here we have the main regression table. As I said before, here we have the intercept and GPA, coefficients, standard error, t-statistic, p-value, lower 95%, upper, and etc. Also, as I see here, there is a repetitive ones, so I delete them. So the intercept, as you know, is the difference between the first data in our data set to the 0 in y-axis. Okay, so this is the intercept. So we know that all the data, the lower, the smallest data that we have in our data set starts from somewhere. The meaning is that there's no matter that GPA is 0 or it's high. Any student with any GPA can get 822 score in SAT. Okay, so there's no matter how much your GPA is, you can get 822 in SAT. So that was the meaning of intercept, and you can see graphically what it means. It's this distance. This is the intercept. Okay, so and there is a coefficient for GPA. So we can have just these two data, and we can have the regression formula. What we will do is that, so we know that y equals to beta 0 plus beta 1 multiplied by x. So in here we have beta 0 as intercept. Our intercept is 822.19 plus beta 1 here is 213 times x. So this is our regression formula in here, and you can see that this is the exact formula that we have here. Okay, so that's why I said you can get the formula in using just a chart, but this works for only one variable regression. Okay, so let's get to the other segments. Here we have standard error, which is obvious, and here we have the t-statistic. So again, we have a statistic, and we have the p-value related to that statistic. So here also you can see that our p-values are too low, so that we can see there is a significant relationship between GPA and SAT. And here, if you get p-values too large that you cannot trust the significance, maybe you should get rid of these independent variables and get to select other independent variables which are more significant in terms of determining the y variable. Okay, so that's what p-value can tell us. So, and here we have lower and upper 95% of confidence level, and what they mean is that all the estimates that we have are beyond these two actually numbers. Okay, so we have coefficient for intercept as 822. This is between these two. Okay, so and then we have GPA as 213. This is also between these two. That's it for the analysis. And if we want to get back to our data to see what do these numbers mean actually for our set of data, is that here any number that each person gets in GPA scores. So if you get GPA at 1, you have to multiply 213 to 1, and you have to sum it up with 822 to get the SAT. So in here, our SAT is the GPA score, okay? GPA score times 213 plus the intercept 822. Okay, so here, as I mentioned before, we know that if GPA is 0, we still get 822 as the SAT score. So the other thing I wanted to mention here is that this GPA coefficient is also can also be interpreted as the slope of this line. So graphically, we know that we have a regression line. Okay, let's get another one. So if this is our regression line, then we know that this distance is intercept, and then we have this let's say beta 1 as the slope of this line. This is the slope of this line, and interpret as the coefficient of the independent variable, which here is 213. So that's the graphic imagination of this data. The other thing that also I wanted to mention is that if you want to know more about Anova, please go check out my video about one-way Anova. I'm actually in process of making the other videos for two-way Anova also, so go check them out to see how maybe that can help you also. And also please go check the regression formula in Excel video that I had to see maybe if this one can also help you. So I guess that's it for today's video. I hope you learned something new. Please don't forget to give this video a thumbs up and subscribe to our channel. I will see you in the next video, and bye.